All right, I have a bunch of toys that I am excited to be showing some of the optics effects that we did. And so let's talk a little bit about image formation. And to do that, I gotta change the lighting. Not that much. So 1 off, 2, come on, 2 on, 3. And so we're going to send both camera and content. So you should be seeing 2 different images on the screen right now. In one case, you're getting the great. So you can see me at a table working on the optical bench. And then you're also seeing the view from this camera looking down the optical bench at the target. And so I want you to be able to see some of the images that we're talking about being able to form. So I have a target here with a little light that I can turn on and kind of make bright and show what's going on there. So a convergent lens, something that you're maybe familiar with from magnifying glass, when it's close, this is giving a upright image of that 4. So it hasn't changed much, it's just gotten a little bit bigger. Now, if the lens is right next to the object, the 4 is the object, it doesn't change the size much. As I pull this lens away, you can see that 4 get larger and larger, still upright, but it doesn't completely fit inside, the image that we're seeing through the lens. Now, if I stick my head right down there and kind of look through, I can see the whole 4, but what you're getting from the camera is a magnified view that's upright and harder to see all of it. Now, the focal length of this lens is 20 centimeters, and so this distance, if you look on the right camera, when I get to about 20 centimeters, you'll notice that the image there is so magnified that we've basically washed out. You're seeing a very, very small part. And then if I keep going, now the image is actually upside down. So what we're seeing here is that upside down force. So we've gone from a kind of real image to a virtual image there. And it's not really clearly in focus at the distance of where the camera is. If I put a screen in here, now I can start looking at trying to find the spot where I get a sharply focused image. And if you'll give me just a sec, I want to turn off the lights, some of the lights for this part to help that show up. Not those ones. Doing optics requires a lot of the control of lighting. So I can find a spot where I can get kind of the best projection of, notice how the 4 is blurry here, kind of comes into focus, and then gets blurry here as I'm moving this screen around. So I'm projecting it, and here's my best spot. Now, if I move my optics, if I move this part, now I'm changing the magnification on the 4. I also change the place where it's most in focus. So it's fuzzy there, it comes into focus, and then it goes out of focus and gets fuzzy again. And so when we talk about image distances and object distances, this is hopefully giving you that sense. This is my object to the lens, so that's my object distance, and then my object to the screen is my image distance. And you can see something when you're not exactly at focus point, but that kind of perfect image, the best that you could do is when you line this one up exactly. Now, this is a converging lens, and I can have these kind of different regimes. I can have an upright virtual image. I can have a magnified real image. And then further out, I start getting something smaller. And now the distance here is such that the focus is actually behind the camera. The camera is attempting to focus. This is complicated by the additional lenses in the camera, but the camera is attempting to focus and can't because it's behind. Now I can also have not just convergent lenses, but divergent lenses. And here I'm actually going to turn off the light to make it a little easier to see that 4. And if I move this in front, you can see there's the 4, and there's a 4 with a divergent lens in front. Now, when the divergent lens is right there next to it, it doesn't have much of an effect in terms of magnification. Sorry, let me turn one set of lights back on so that the camera stops freaking out about the low light situation. I'll make it a little easier to see the 4. So there's the 4 no lenses. This is a divergent lens that I can insert in, and it makes the 4 smaller. And the further away it is, I can get this smaller effect being right next to it. Not much of an effect, but now as I increase my object distance, I end up getting this bigger effect, a larger effect of this lens. You can see here's the 4 without the lens. Here I'm about half a meter away, and I'm getting a lot of shrinking. Now this is always a virtual image. I can't project that 4 through a divergent lens. You can see it looking down the beam, but I can't give you a 4 here projected in such a way that the camera from the ceiling will see it on the 4. I can combine lens systems if I have, for instance, just the convergent lens giving that effect. If I insert a divergent lens into the beam path, now I'm suddenly getting an upright image again. And so in this case, the object distance to the lens, hey, not right now, doing class. The object distance to the lens, then I could calculate an image distance to that lens, and then that image would be my new object for the second lens in the system. And so these systems of lenses, which we didn't get into, are just sequential applications of this 1 over s plus 1 over s prime equals 1 over f equation, where an image in one situation becomes an object in the next situation. And we'll come back to that with 2 convergent lenses in a little bit, but I want to show a couple other things that we can do. So I have on here a collection of, sorry, go back to this one. I have two bright lines. I've just put a different thing there, and I'll magnify that for you so that you can see that there's two lines and a thin black slip between them. And now I also have this wheel, which has apertures of different sizes. So I'm showing you, I'm not yet passing the path through, but we're starting with, there's a big hole, and I can kind of dial that down to a bunch of different holes. So let me create an in-focus image of that aperture that we can see. I got to change the light again. Change the camera just a little bit. Zoom out. And sorry, you still want to see both of those. I want to change that to there. So what you're seeing on the screen, I can make that out of focus. I can bring that into focus. So here's two lines where we can see that black space in between the two lines. So that lets us know that we're in focus. I'm going to turn on a light so you can kind of see. So this is the situation we have. We've got the source, the lens, and then the screen that I'm projecting that image on. Now I'm going to add an aperture in front of the lens, and I'm using the largest hole on the aperture. And we still have an in-focus image. But now I'm going to deliberately defocus the image. Let's go. So there I am in focus. So I'm blurring that out. It's now harder to see what's going on there. But remember, that's the big hole. I'm going to take it down to, from the big hole to a slightly smaller hole, and watch what happens to the image on your left. As the hole gets smaller, the image is getting dimmer, but you're also starting to see that dark line in the middle. So with less light coming through, let me show you the aperture that we're at right now. So I've decreased how much light is coming through compared to this aperture, and the effect on the screen as we go down is the image gets dimmer, but we start being able to see that black line in the middle as less light from different focal points is being smeared out. Now, I want to show, here's the other thing about apertures that we kind of talked about was not just the effect of sharpening and dimming images, but what does it do to the image? So I have an aperture here that's a half circle, and I have an aperture here that's a whole circle. So let me come back to our favorite 4. I have the whole circle aperture. I'm going to bring that to in focus. So we have a sharp 4 on our screen, and you can see that on the right or the left. Let me highlight open circle, seeing the 4, and now I'm going to shift. And now we have a half circle aperture. I'm still seeing the entire number 4 cleanly on the screen, even though I've blocked half of the lens. Every part of the lens is involved in focusing light from my source. From my source, it strikes every part of that lens and then moves on and is focused down onto the screen. If I block part of the lens, the other parts of the lens are still grabbing the entire image. This is counterintuitive. Sometimes graduate students in physics programs, so PhD students in physics, run through this and they're like, oh, so if you hadn't seen it, don't feel bad that that wasn't an intuitive thing for you, but now you have seen it. So I hope that that helps you kind of lock onto things. All right, that's apertures. We've got a bunch of stuff. Any questions about the image formation with those kind of first things? I want to show, I want to show so much. I want to show you telescopes too. That's a convergent lens because I was able to focus an image onto a screen, and that only happens with a convergent lens. A divergent lens won't give you a real image. All right. Windows are open. So now let's look at a telescope. So what I'm looking at right now, let me give you the wide view. So the camera is now looking through one convergent lens and another convergent lens. And the effect of that, the first convergent lens is creating a virtual image that is then the object of the second convergent lens. Sorry, it's going this order. So the window's out that way. And that's focusing in on, the next convergent lens focuses in on that image and uses that as the object to create the next image. And so what you're actually seeing, and now I have the camera looking out the window. So let me show, we're looking out a window and the camera can zoom in. You're off there. So here's the window that we're looking out of and how big it looks. Now I'm trying to set roughly the same zoom on both cameras. And you can see there's a height difference between what the first camera sees, the do not enter sign, is about half the height of what the other camera sees. Now, if I go to kind of a little more easy to kind of see in context what's going on there, this is roughly what I see by naked eye, the difference between looking through the camera, looking through the telescope or just looking out the window. There are size differences at kind of equivalent zooms. This is where the two cameras come in. So this is an example of magnification. So we would look at the vertical height that we're getting, and I could say that that's twice as high as the thing that I'm just looking at, and that tells me that the magnitude of the magnification is 2, but it also, because it's upside down, there's a negative there. So that would be a negative 2m. And for a telescope, your magnification is the ratio of your two, lenses. And so the lenses on this table, this one has a focal length of 20 centimeters, and this one has a focal length of 10 centimeters. And so the magnitude of the magnification, 20 over 10, would be the 2 that we see on there. All right. Oh, so much to show, so many toys. Let's pop over and show. I want to do diffraction, and then I want to talk about polarized light. So I got to put, we might be able to do it with this much light. So new camera angle. And let's, yep, that's the wrong. All right. Pop over to just show that one. What we have here is another light source. And I've got a blue LED down at the bottom. And then what I'm going to add in front of the actual camera, I have a little diffraction grating here. So you can, when I'm holding it there, it looks clear. I've got some tape because I'm going to actually tape this in front of the camera. So this is not a single slit, this is several 100 lines per millimeter, and the effect there is that we start to see these side peaks. Now, when I'm sitting in the room, like there's a peak right on me, I don't actually see that light. I can see that it's here because I'm looking at a screen, and I can see the other one over here because I'm looking at a screen. But those are both coming out of this being diffracted for the camera into these side peaks. And if I block just the middle one, they all go away. Now, what I want to show here is try and remember the position of that light, and then we're going to change the wavelength. I'm going to go to turquoise, and then green, and notice it's moving a little bit further out. So as the wavelength is getting longer, the placement of that light relative to the other ones starts being a little bit further out. And you can even see that in individual colors. Now this is a yellow light LED, but it's not monochromatic like the lasers that we used earlier. And so you see a little bit of green, but also a little bit of red. And notice that that red is further out compared to the green. And so we can stack that a little bit more. There's orange. So as we change the wavelength, we're going from closer in to further out. Here's a deep red. And now I've got right at the top all of those colors, including a white light LED. So the white light is built up of this range of colors. It's a bunch of different lights, whereas my other lights are, to have that kind of defined color, are narrower, but they're not as narrow as, for instance, laser light, which would be a specific wavelength. I did that demo back when I was teaching in the pod. But this is an example of the wavelength affecting how diffracted the different colors are going to be. All right, that was the diffraction demo. We've got one more big one. Oh, You can also see I've turned on the room lights, and they're fluorescent and also diffracting, but I imagine that diffracting is distracting, so let me take that off and give you a clean 4K image of our polarizer. Now this is a physical polarizer. I have the ability to change the orientation of the polarization and then send a wave down through all of those. Now, this is not how electric fields and light would definitely look, but I want to kind of show what's happening here with the polarizer. So I'm creating vertical polarization with this. Even if I tried to make, for instance, a circle or other forms of polarization, what I'm passing from this one is vertical polarization. Now I've set it so that this one is going horizontally. And so if I send a horizontal wave in, you can hopefully see that it's passing through the first polarizer, but when it hits the second polarizer, which is vertically oriented, not much wave gets through beyond that. So you can see it vibrating there, but not in between number 2 and 3. If I then change the polarization of this one to be half, or to be horizontal, now my vertical polarization gets through, but stalls out here. But if I go at 45 degrees, now before, I had nothing getting through the vertical polarizer because I was coming through with horizontal polarization. I'm still going to be starting with horizontal polarization, but the effect of that middle polarizer is to take that horizontal polarization and give it some vertical oscillation. I've broken the horizontal vibration this way into components vibrating this way and vibrating this way, and, sorry, into this way and this way at right angles. And so this component of this vibration gets through. I'm letting this vibration get through on that diagonal, but this diagonal can be broken into vertical and horizontal components, and the vertical part can then get through. So if I just had two polarizers, a horizontal and a vertical, nothing would get through. But by adding a third polarizer, a third filter, I'm actually letting a signal get through my final stage. Questions about that? All right, it is 1:41. The quiz should now be live on Blackboard. Thank you very much for coming out. I hope this was a helpful illustration of some of the stuff that we did in optics at the end. I will be posting the video in the chat. If you want to review any of this later, feel free to shoot me emails, swing by office hours next week, and all else failing that, I will see you for the final on next Friday. Thanks.